All right, so this time we're going to talk about symmetry in functions. In particular, we're going to be trying to get at what is a group? What's a group about? So let's remember what a symmetry is. It's kind of a way of moving a thing back onto itself in a way that doesn't change the thing, so that the thing is then invariant under that transformation. This idea of moving an object back onto itself, we can think of as a function from the object back to itself. So let's see an example. Here's our favorite tetrahedron. And if we want, we can think of a function from the tetrahedron to itself. And what this function is going to do is flip over the green triangle that I'm sort of drawing inside. And this is going to be the flip that changes A and C, but leaves B and D alone. And it's a very special kind of function. It's a length-preserving function, so that the tetrahedron, everything sort of maps into the same place. Nothing's sort of distorted or anything like this. Now there's a really special function called the identity function that leaves everything alone. And indeed, leaving everything alone is a way to move everything back onto itself. So that's a good symmetry too. Now I want to remember that, if you have some functions from an object to itself, you can compose the functions. So here we see that there's, an f and an h is going to be the one that flips C and D while leaving A and B alone. And if you compose the two, you get h of f. H of f is itself also a symmetry. We haven't changed the tetrahedron. That's pretty cool. This is going to be really useful to us later. Now let's remember the perfectly symmetrical face, that guy that we started with a while ago. You flip it over and it stays the same. You can flip the notion of left and right. We have the identity, but we also have the flip. It's a very, very simple kind of symmetry. And if we flip it again, we get back where we started. So then we can say that flip of flip is equal to the identity function. That's pretty cool. Now let's think of it's sort of a square with some bumps in it. And this is going to be a very nice sort of object. It has a top, and like before, it has a bottom, and we can rotate it around, but we can't flip it over anymore because of the bumps. So this one only has the 4 rotational symmetries, including the one where you leave everything alone, the rotation by 0 degrees. So if we draw this initial state with the A up in the left-hand corner, we can rotate. And then the A is up in the upper right-hand corner, and then we rotate again. And now the A is in the lower right-hand corner, and then we rotate again. And now the A is in the upper left-hand corner, or lower left-hand corner, and then if we rotate one more time, we're back where we started. R, 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 R. And we see there that r to the 4th is equal to the identity function, that one that leaves everything alone. If we do r squared and then r squared again, we end up at r to the 4th. If we do r cubed, then r squared, then we get back to r. That's interesting. And in fact, just like, if you think of your multiplication tables, we can make a composition table for these different functions. We see that, r squared is equal to r to the 4th, or the identity. And we're able to see that r cubed followed by r is equal to the identity, and r followed by r cubed is equal to the identity. The identity composed with anything just gives the same thing back, and so on and so forth. You can fill out the rest of that. Now your exercise is going to be to build a composition table for the symmetries of the equilateral triangle. There's 6 different symmetries there. How do they all come together?